Ooh, I think I'm recording. What's going on, everyone? Welcome back to another phenomenal and fun biochemistry video. I apologize for not being able to meet with you guys sooner and having to do a video. I know we had school canceled on Monday, which kind of threw a wrench in a lot of our plans. And also, Goo is kind of having a weird biochem schedule this try. For you guys, I'm sure you guys have noticed it getting a little bit ahead in some information, even in biochem too. I mean, the video I had recorded just a little bit ago, the amount of information, extra information I had to throw in for exam two was not very similar to previous tries. So I had to do a little bit extra reading and everything like that. And also too, this is the first time I am, I guess, tutoring this section of material. Um, I guess for the first time this try. It's been a little bit since I've covered this information. So I have made a collection of a couple of examples on problems you guys are going to see in relation to carbohydrates and plopped them in this document. So we're going to be going through that. Um, and realistically, this is just going to be a huge overview. And I know, as you guys know, I mainly stick to this Teresa Porter packet, and this is basically what got me through biochem. And I know a lot of you guys have been going to Annalise as well, and she does a phenomenal job at describing the inner workings of it because realistically, I am not a biochemistry expert, as I've said before, and I just kind of go through the information I learned, the information I need to know for biochem and what helped me get through that. I just kind of relay that information back to you guys and hope it helps. But with you guys going to Annalise as well, I'm sure you guys are academic weapons right now and try to gets busy. So I guess let's get into it. So in the previous video that you guys watched, I covered a lot of this stuff, going through the information. And again, this was a video, the last video was one I made last trimester for, I think, a weird spring break thing. I forgot exactly. So I believe it covered everything up to this point. I'll have to go double check and I might have to throw out an extra video just in case. But today we're covering carbohydrates, and carbohydrates are pretty cool. We're going to be talking about glucose a little bit, and especially when you guys get into next trimester with Biochem 2, glucose is going to be a heavy component, and a lot of the stuff you're learning right now will come back to haunt you next try. So make sure you absorb it well into your brain and absorb it like a sponge. But sorry, I had to drink a little bit of coffee there. I'm starting to run out of some gas. All right, carbohydrates, building blocks. We know carbohydrates are made from simple sugars or monosaccharides. Another big thing we need to know is they are water soluble. And one of the little things we do have to memorize, just as a fun fact, is just this molecular formula for simple sugars. We know that the number of carbons will just be related to by N. H, or the hydrogen count, will be represented by 2 times N, and then oxygen will just match the exact same as the carbon count in the structure. And then if we look down here to this little chart right below, we can see that we have different N counts. So if we look at the first one, N is equal to 1, N being the representation of carbons in the structure. With only one carbon, we cannot count this molecule as a carbohydrate. It will be referred to as formaldehyde, and granted, we do not need to know formaldehyde or acetic acid for this class, but what we do need to know is as soon as the carbon count reaches 3, that is when a structure is referred to as a carbohydrate in reference to this little, oh, where's my laser pointer? This little equation right here. So as soon as this N right here reaches 3, we can start considering this structure as a carbohydrate. And if we have a structure with 3 carbons, it will be referred to as a triose. And if you guys want to memorize these, glyceraldehyde, deoxyacetone, glyceraldehyde will make an appearance next try, but this try, historically speaking, as I say, I've never seen anything about glyceraldehyde or a triose, but now when we get up to a carbon count of 5, we're going to be referring to the structure as a pentose, and pentoses are commonly used for ribose, deoxyribose. Ribose is used in nucleotides, and you guys will learn next try about the pentose pathway and how it gives out all of these, why can't I think of the term? Metabolites that are used for anabolic pathways for building larger molecules. Again, that information is a little bit more advanced and not needed for this class, but I always like to branch it into future knowledge because I do enjoy this stuff. I might not have the deepest understanding of it, but I like how it all relates to each other. So next little thing we'll look at is when the carbon count reaches 6, we will refer to these molecules or compounds as hexoses. These will be considered simple sugars, and this biggest example we have is glucose. Now, these next couple of pages, and again, there's a lot of information in here. These next couple of pages are going to be talking about linkages and different names for different molecules that we're going to go through. But I've made these little reference boxes over here for myself, and which made it super easy to learn all this information. So that is what I'm going to be referencing on how to navigate some of these problems that we're going to be looking at. And then I'll just do a quick run through of the diagrams that are in Teresa Porter's packet and just kind of talk through those as well. But I just like using these little boxes right here because it just simplifies all the information and tells us exactly what we need to know. So let's talk about right here. So you are going to be seeing a couple, I guess, polysaccharides and the use of different building blocks or monosaccharides. And when they become combined, they can form larger molecules known as polysaccharides. So building blocks that we need to know glucose, galactose, fructose, and ribose. These 4 building blocks will be used interchangeably to create different molecules, and they all, when they're combined, and you guys can see maltose, lactose, sucrose, cellulose down below, we can have similar compounds creating, like if we look at maltose to begin with, we can see that is made by the combining of 2 glucose molecules, and they are combined with an alpha 1,4 linkage. And we will get into these linkages in a sec, but we need to know the different types of linkages within these different polysaccharides. So maltose is built by 2 molecules of glucose combined by alpha 1,4 linkages. Lock that into your brain. Now we have lactose. And lactose is made by a combination of a molecule of galactose and a molecule of glucose, and these are connected by beta 1,4 bonds. Now, what we do need to know about beta 1,4 bonds is they are not digestible within the human body. But with that fact being true, lactose is a little bit of an outlier because some of us contain the enzyme, I believe it's lactase, that can break down the beta 1,4 linkages in between galactose and glucose and break down lactose. So this is kind of where the lactose intolerant people and the people who are able to enjoy dairy products pain-free, this is where the little bit of a war starts because, hey, why don't we have that enzyme? But we just need to know lactose is made by galactose and glucose and combined by a beta 1,4 bond, but this beta 1,4 bond can be broken down by the enzyme lactase. Now we get into sucrose. Sucrose is formed by a combination of glucose and fructose, and the bond structure that we need to know is an alpha 1 beta 2 bond. Now, with it being a beta 2, all betas, beta 1,4 bonds are indigestible, but for this one, sucrose, we are able to break down sucrose, and sucrose can come in a couple different forms. It can come in a mixture or this polysaccharide. Now, when the sucrose is in the form of a polysaccharide through the combination of glucose and fructose, our body does have to break down this bond first before we can isolate glucose and fructose to absorb them into our body. But main thing we need to know, sucrose is made by glucose and fructose and combined from an alpha 1 and beta 2 bond. Now we get into cellulose, and what you guys may notice is, hey, it has the same monomers as maltose, and that is true. But the one thing that differentiates the name is the insertion of beta 1,4 bonds. And as I said before, beta 1,4 bonds are normally indigestible within the human body. So you'll notice this is like, if you guys want to go eat some grass outside, more likely than not, you guys are not going to be able to digest grass if you go outside and munch it right now. And that's because we cannot, as humans, break down beta 1,4 bonds unless we have specific enzymes in our body that allow us to do so, similar to lactose. So with that building block and polysaccharide formation out of the way, we can just move into some weird fun fact information. And again, I like referring to Biochem 1 as fun fact information because that's really all it is. When you guys get to Biochem 2, a lot of it is all continuous structures and everything builds on each other. And I will admit it is a lot easier to comprehend Biochem 2 information compared to Biochem 1, since Biochem 1 is all over the place. So these axial and equatorial chair configurations, which these are just for those with a chemistry background, these are just different conformations on how some of these molecules are set up in reference to chair configurations. And fun fact information that we really need to know is alpha glucose, or this axial formation right here, which we can see it's an axial formation due to this OH group popping out on the bottom of the chair structure. These structures are going to appear, or this structure of glucose is going to appear about 33% of the time. Now, if you go over here and look at the equatorial chair conformation, we can see that this OH group is shifted off and up to the right, and this is referred to as beta glucose, and this conformation or configuration is going to appear 66% of the time in naturally occurring glucose. Now, historically speaking, have I seen a ton of questions on this? No. But is it bad information? No, not at all, because I mean, knowledge is pretty cool. So we've covered building blocks and what polysaccharides they can make and what different bonds are associated within each of these polysaccharides from different combination of building block molecules. We've covered axial and equatorial chair conformations and the percentages on which these are naturally occurring in the environment. And now we get to move on to counting and naming some of these oh, whoa. What just went on? Oh, I must have drew over this in white. I apologize. So basically what you guys are going to see, and if you look at this little structure right here, Dr. G is going to give you a question and say, hey, name this molecule. And it might seem intimidating at first, but these little boxes I drew off to the side kind of make it pretty easy on how to name some of these molecules. And again, these are just going to be multiple choice questions. You're going to see a structure very similar to this, and we are going to go through the steps on how to name it. So, steps in finding molecules. Let's see if I can zoom in here. And I'll leave that little example right there. First thing we want to do is look for what we call an anomeric carbon. And an anomeric carbon, in reference to one of these ring structures, is a carbon that is has two oxygens attached to it. So first step is to always find an anomeric carbon in these structures. And if we look at this little example right here, I do already have it numbered, but what we should be looking for is this carbon right here. And if you guys do not have a chemistry background, these little arrows, or these little corners, do represent carbons in ring structures. So step one, find the anomeric carbon. We can see right here we have an oxygen going right here attaching to this carbon, and we can see we have another little oxygen group right here coming up and attaching to this carbon. So this will be referred to as an anomeric carbon. Now, since we found the anomeric carbon, that is always going to be our number one molecule, or our starting point. And from here, we are going to count the carbons in a clockwise formation. So you can see on step number 2 here, count the number of carbons. And very similar to how we talked about carbon counts up here, this is how we are going to be naming these molecules down here. So start off with the anomeric carbon. We can see carbon 1, carbon 2, carbon 3, 4, 5, and 6 up here in this little branch off group. And with this structure containing 6 carbons, we can refer to this molecule as a hexose conformation. Now, if it only had 5 carbons instead of 6, it would be referred to as a pentose. If it only had 3 carbons instead of 5, it would be referred to as a triose. And so now we know we have 6 total carbons, and we know this structure can be referred to as a hexose. But there's also a little addition to the name that we need to throw on there, and this is reference to these CH groups popping up. So you will see examples where you have 1 of these popping up, or you have 2 of these popping up. Now, if you only have 1 CH group popping up right here, very similar to this example, we will refer to that as an aldose. So these hexose and aldose will be combined, and with 6 carbons being in this structure and only 1 of these CH groups popping up, we can refer to this structure as an aldohexose. So if we run through it again on how to find these molecules, step 1, look for the anomeric carbon, the carbon bound to 2 oxygens. Number 2, starting from the anomeric carbon, count clockwise in a clockwise direction to figure out the total number of carbons you have in the structure. Once you have figured out that, look for the total amount of CH groups popping up here. And when you determine if it's 1 or 2, we can come up with the full name. So if we have 6 carbons, we refer to that molecule as a hexose. And if we have 1 additional CH group popping up, we will refer to that as an aldose. So when you combine the two, it will be an aldohexose. Now, in this little example that I went and found for you guys right here, this is a little bit different. So this example has 2 CH groups popping up right here. And this will be referred to as a ketohexose. And for this example too, how I always like to look at it is when we do have an additional CH group popping up on the anomeric carbon, we do count this a little bit differently. So instead of having our anomeric carbon starting right there at this little carbon right here and starting our count there, we actually start our count with the CH group popping up instead. So we know we have an anomeric carbon right here, but instead of counting that as number one, we pop up here and count that one as number one. So one, two, three, 4, 5, 6. So we know we have 6 carbons in the structure, which we'll classify as an hexose. And then we look for the additional CH groups popping up, and we have one CH group right here and one CH group right here. So with 2 CH groups popping up right there, we know it is going to be referred to as a keto. So this will be referred to as a keto hexose with these 2 CH groups popping up. Compared to here, which is an aldohexose with only 1 popping up. But when it comes to naming these molecules, it is pretty straightforward. And if you guys can gather this concept and have a good understanding of this concept, then these questions should be layup for you guys. I know going through the exam, I was so grateful to see these questions, especially with my roommate and tutor, Tim. He prepared me pretty well for this, so I am grateful for that. And I'm actually basically copying his entire tutor plan for Biochem 1. So props to him. So moving on, we've already covered how to name and find what type of molecule we are looking at. And now we are going to be getting into different linkages within these molecules. So linkages are basically how we make polysaccharides. And it's very simple to these little linkages we saw right here and how we link monosaccharides together to form polysaccharides and larger molecules. We're going to be figuring out how to name it, whether it's a beta or an alpha. And I will admit, some of these polysaccharides that we talked about right here are a little different in the rules when it comes to their classifications, but for the examples you guys are going to see, what I'm going to explain to you guys is all you need to know, and I did include some examples that we are going to walk through. So again, step one when it comes to linkages is we are going to be looking for the anomeric carbon again. And once we find the anomeric carbon, we are going to count the number of carbons. Basically how we want to do is we want to just label all of our carbons. So we'll look at it right here. So we can see that we have a linkage right here. And actually, I did get a little bit too ahead of myself. We are going to be talking about the different kinds of linkages between alpha and beta. So anytime you guys see a U-shaped linkage right here, we just want to refer to it as an alpha bond. And anytime we see a little zigzag or a weird bond right here, we are going to refer to it as a beta bond. And basically how we are going to name these linkages is whether or not they are attached to an anomeric carbon or a non-anomeric carbon. Anytime any of these linkages are going to be referred or linked to an anomeric carbon or the carbon that is bound to 2 oxygen molecules, that is when we are going to be using the alpha and beta classification. However, if we have a linkage, and actually right here, if we look at this example right here, we can see that we have an anomeric carbon right there and an anomeric carbon right there, but this linkage is not attached to those anomeric carbons. What this means is we cannot use these little alpha and beta labels for these linkages. So instead of like this example right here to where we have the bond right here on this anomeric carbon or carbon number 1, and then we have it coming up here to carbon number 6, we know that the start of the linkage is at this first anomeric carbon right here, or carbon number 1 on one of the structures. And then this bond comes up and attaches to carbon number 6 on this other molecule. So the way we would classify it as is an alpha 1,6 linkage, because the first part of our linkage is on an anomeric carbon or carbon number 1, and therefore we can give it an alpha classification because it is bound to an anomeric carbon. But we look over here and the end of the linkage is attached to carbon number 6 on this next structure, but that carbon number 6 is not an anomeric carbon or a carbon bound to 2 oxygen molecules. Therefore, we cannot give it an alpha or beta conformation. So that is why we see alpha 1 for this alpha 1 linkage bound to an anomeric carbon, but it's alpha 1 and 6 because this 6th carbon is not an anomeric carbon, so we cannot give it an alpha or beta label. And following up on that concept, we can look down here and we can see that this bond right here is between carbon number 2 and carbon number 2 on both of these structures. And both of these number 2 carbons are not anomeric carbons, so we cannot give it an alpha or beta label. and therefore this linkage right here will only be referred to as a 2-2 linkage. And if you guys have been doing your practice problems pretty diligently, you guys will see that these examples are very similar to the examples you guys are going to see in your exam. And that is why I like usually going through them in person, because no one can, you really can't learn how to speak Guttweiler unless you actually look at the verbiage of his questions. But these are the structures that you guys are going to give. And I hope I am being pretty clear on my explanations of a lot of these different linkages going through some of these molecules. And I know it's a lot more difficult just to say these concepts in video rather than person and have clarification questions. So I do apologize for putting out this video late, but if you guys do have any questions, please feel free to shoot me a text. I'd be more than happy to clarify some of these explanations. So now we're going to kind of go through some of these just different polysaccharides, and we've talked about fructose. We've already kind of walked through anomeric carbons right here and how to count in a clockwise formation. So now we're going to get into some of these polysaccharides or disaccharides, and we've already talked about maltose and how maltose has an alpha-1,4 linkage between glucose and glucose. And again, right here, I know this is where I'm talking about how these polysaccharides kind of break the counting carbon terms that we've been talking about. But realistically, all you need to know for maltose is the alpha-1,4 glycosidic linkage. When we go to lactose down here, we know it's between alpha-glucose and galactose. And we know these have a beta-1,4 glycosidic linkage. And again, this is where you see that little zigzag line representing a beta linkage. We come down here to cellulose, and we know again it's a polyhomomer of glucose, except we have a beta-1,4 glycosidic linkage here. And again, if we remember, beta-1,4 linkages are not digestible in humans, and that is why we can't eat grass. And then we have sucrose right here. And sucrose is just a combination of glucose and fructose with an alpha-1 beta-2 bond. We do have two different anomeric carbons here, and I believe Annalise definitely knows this a lot better than I do. But when it comes to why it's a beta-2 linkage on the opposite side of this fructose right here, I believe because it's flipped and it twists the bond, so it's kind of an alpha-1 on one of them and a beta-2 on the other. But for what you guys really need to know is you just need to know sucrose has an alpha-1 beta-2 bond. So carrying on, let's see if I missed anything here. Nope. So now we're going to be getting into homopolymers of glucose, and we're going to be talking about starch, glycogen, and cellulose. And there's just a couple differentiating factors between these three molecules or homopolymers that we do need to know. So we need to know starch has a carbon count between 18 to 20 carbons, and it is mainly composed of alpha-1,4 and alpha-1,6 linkages. But main thing you guys need to know is no matter how many branches of starch there will only be one anomeric carbon. Lock that fact into your brain, because on those word bank questions, I've seen this come up on my exam. I've heard it come up on exams in the past. So we need to know starch only has one anomeric carbon no matter how many branches, and we need to know that the anomeric carbon is the reducing end. So therefore, if we only have one anomeric carbon in the whole molecular structure of starch, we know we're only going to have one reducing end. And we need to know starch is made up of alpha-1,4 and alpha-1,6 linkages. It is found in plant life, and we have two components of starch we need to know. We need to know amylose and amylopectin. So we know amylose is going to be a small polymer, and amylose is only going to contain alpha-1,4 linkages. We need to know amylose only has alpha-1,4 linkages. And then we have amylopectin right here, and amylopectin is a combination of both alpha-1,4 and alpha-1,6 linkages. So starch can have alpha-1,4 and alpha-1,6 linkages, but the main differentiator for this one is it's only going to have one anomeric carbon and only one reducing end. Now, after talking about starch, we're going to go into glycogen. And glycogen is found in animal life. It's found in carbohydrate storage within our muscles. This is going to be a concept you guys are going to be talking about next trimester, but it's never important to know now. And the biggest thing we need to know is glycogen has more alpha-1,6 linkages than starch. That is one of the biggest facts you guys need to know for glycogen right now. And it also has more non-reducing ends. Increased non-reducing ends increases the fuel that can be used by the cell. And these two highlighted little facts right here is something that you guys need to know, especially for those word bank questions. He will throw these little weird definitions out here, and you guys need to be able to differentiate between if it's starch, glycogen, or glucose or cellulose. I apologize. So another thing we know is glycogen only has a carbon count between 8 to 10, and it's found in skeletal muscle cells, as I said earlier. Yeah, besides that, that's pretty much it. And now we get into cellulose, and cellulose is beta-1,4 linkages. We've already covered this, but cellulose really only contains beta-1,4 linkages. We know we cannot digest beta-1,4 linkages between glucose, and as I said before, we can digest the beta-1,4 linkages between glucose and galactose with the enzyme lactase. And cellulose is mainly just a dietary fiber, and it's another homopolymer of glucose because realistically, we only have glucose molecules making up this structure. Yeah, besides that, big key points. Starch, 1 anomeric carbon, which means it only has 1 reducing end. It's made of alpha-1,4 and alpha-1,6 linkages, with amylose containing alpha-1,4 linkages, amylopectin containing alpha-1,4 and alpha-1,6 linkages. We talk about glycogen, and we just need to know it has more alpha-1,6 linkages than starch, and it has more non-reducing ends. And it's found in skeletal muscle. And then cellulose, we've talked about cellulose quite a bit already. Just main thing that we need to know for that is beta-1,4 linkages. And normally at this point, this red line right here dictates the cutoff for exam 2 content. However, I did talk to a couple of you guys, and it seems like you might be throwing on a couple additional information. So we're just going to cover basically what you guys have covered so far with Dr. G in class. So alcohol sugars right here. I have not seen too many questions pertaining to alcohol sugars, but biggest thing we need to know is they end in "ol." Anytime you see an OL, we should know it's an alcohol. That's really all you need to know for that. So now we talk about high fructose corn syrup. What we need to know is high fructose corn syrup is made from a mixture of glucose and fructose. And if you guys remember sucrose, that is a molecule that has bonds between glucose and fructose. And if we jump back up here, we can see that sucrose is bound by alpha-1 and beta-2 linkages between glucose and fructose, but high fructose corn syrup is a mixture and not a polysaccharide. Therefore, we do not need to digest it because when we digest stuff, we break the bonds in between these individual structures. But with glucose and fructose just being mixed together for high fructose corn syrup, there are no bonds for us to break. It is very high on the sweetness scale, and then honey is also another mixture of glucose and fructose, which makes it very sweet. And as I just talked about, for sucrose, compound of glucose and fructose, and needs to be digested because it is compound. Sweetness scale right here, we just need to know sweetness is measured on a scale based on dilution. Sweetness, again, is how sweet something is within our mouth. Sucrose is measured at 100, and it's based on a dilation scale. And I personally have never referenced this chart too much. I just know when it comes to sweetness, sucrose is one of the main things we're going to be looking at for being super high on the sweetness scale. And then we also have sorbitol, which I've maybe seen one in a blue moon question about sorbitol, but it is made by reducing glucose and fructose, with glucose being an aldose and fructose being a ketose. Again, I've not seen too many questions on this, but it is never bad to know and understand. So with sweetness scale out of the way, we can just move on to glycemic index, which I believe is where you guys kind of ended off. And when it comes to questions you guys are going to see, anytime you see anything referencing the glycemic index, we need to know it is measuring everything under the curve. So we can see right here on our y-axis, we have glucose. On our x-axis, we have time. And we see we have this little hump right here. We need to know that the glycemic index represents everything under this curve. And that is just such a key point. And the questions you guys will see about this is in reference to definition questions. So again, area under the curve is going to be a need to know for the questions you guys are going to answer. We know the glycemic index measures carbohydrates, and it's a really good tool for indicating blood sugar when carbohydrates are digested. And when it comes to glycemic index, our baseline of measurement is going to be everything referenced to glucose. Glucose is going to be one of our main references. And you guys, again, will see this next try with trying to raise and lower blood sugar with all these different molecules in our body. Everything is referenced from glucose in that example. So another big component that we need to know are the axes. And we just need to know time is on the x-axis, glucose is on the y-axis. We need to know glycemic index covers everything under this little curve right here. And then we can even see over on this little chart right here with the glucose concentration. Again, glucose on the y-axis, time on the x-axis, and you will see all these different curves right here. And again, this glycemic index is measuring everything under this curve. That is a need to know information. And I don't think you guys made it this far into bond dissociation energy yet, but that is a lot of this exam 3 stuff I do really enjoy talking about, and it is a lot of fun. But for right now, between the video I just put out and this video, I should cover everything you guys need to know for this upcoming exam. So again, any questions about this stuff? I know I kind of flew through it, but any question you guys have, please don't be afraid to shoot me a text. I'm always happy to answer any questions, and do as many practice problems as you can, because nothing is going to prepare you more or better than any tutor. The best thing you can do is just rip through those practice questions and do as many of them as you can, because the more fluent you become in speaking Gutweiler, the better off you're going to be. So study hard, have a great Sunday, and good luck tomorrow, guys.